Alright, so last we looked at the print function and the scan function. Now we're going to be doing another problem. This one's going to be dealing in more with how functions work, function prototypes, and other such things you need to know in C. So to start off, we're going to have a problem statement, and it's a person enters a distance they ran in kilometers, convert it to miles, they convert how fast their time was in minutes to run a mile. So for the input, we know we need the kilometers ran, the output we need the miles ran. So the first part of this algorithm, just taking kilometers and converting to miles, that's a pretty easy solution. Should be distance in miles equals kilometers ran times miles per kilometer. And miles per kilometer. There's our little stub. So whenever we open up Cloud 9, it's going to give a second to reconnect me. Type in BC. And it should load up base calculator. Alright. So the first thing is miles. Oops. Just paste that in, but kilometers to miles equals that. That may not work actually. I need to change the precision equals 3, I'll say 10. Re-enter that just to be sure, and let me test it by actually echoing out what's there. Okay, looks pretty good. So now miles ran equals, kilometers ran equals 5, so 5k, and then kilometers to miles times kilometers ran. I was stupid. I didn't store that in a variable, but we get 3.10. And so let's try in 5k in miles. And 3.106, and when we test this out, 3.106, so we know that our algorithm there is working perfectly fine. So we can go ahead and quit out of there. So the first part of our algorithm, very simple, and it works quite effectively. So now we need to solve the next part of the problem. And so we need to figure out how to get the user to put in the correct time, and then we need to figure out how to break it down. So our first stab at it, we're going to input the time to run in time in minutes to run, time in seconds to run, convert minutes to seconds to a common format, and then output the miles ran per hour. And so in my little stub here, I figured out that minutes to seconds is 60 seconds in a minute. And I'm going to use 4 as the distance in miles because that's going to give me an easy number to check against. Whenever you're doing desk checking, it's very important that whenever you're entering in test cases, that you use test cases that are easy to figure out, but also that test all the parameters. And there's 3,600 seconds in an hour. Again, 60 seconds per minute, 60 minutes per second, 6 times 60, 3,600. Pretty easy math. So then for time ran in minutes, I'm going to use 36. 36 divided by 4 should be 9, and time ran in seconds, 20 divided by 4 should be 5. Then I'm going to calculate the total time in seconds, which is going to be set equal to time ran in minutes times minutes to seconds plus time ran in seconds. Now, here we get into operator precedence. C in almost every programming language I know of works off the PEMDAS format. And that is parentheses, exponents, multiplication, division, addition, subtraction. So standard PEMDAS stuff works here. If you need to change the order of operations, so let's say I wanted to calculate minutes to seconds plus time in seconds first, I would need to put a set of parentheses around this in order to make sure that it was actually able to calculate that first and this. Right now it's just going to go pretty much left to right because this will calculate first, then that'll calculate. And then it'll store the value of this calculation in total time in seconds. Then seconds per mile equals seconds an hour divided by total time in seconds. Then I take the miles to total time in seconds and set that equal to total time in seconds by miles ran. Here, this little stub, this is what's known as typecasting. I don't actually need to do this in this case, but if you have a floating point number And you need to make sure that whenever the machine by default, if you try to use both integers and floating point numbers, it will go ahead and behind the scenes convert the output usually to the floating point type. If you want to stop that, then you need to typecast it and tell the machine explicitly, the compiler really, explicitly that, hey, I want this to be integers, do not do the conversion. In this case, it's actually unnecessary, but I went ahead and put that anyway just to show it. So if you see int or float or some other thing in parentheses like this, that's what it's doing. It's typecasting this variable. The next thing that you haven't seen before was known as the modulus operation. And the modulus operation, if you divide integers, you normally get a remainder. The modulus is asking what is the remainder of this calculation. So there's my first algorithm, and it's a pretty bad one, but just for demo purposes, it is the kms2miles.c file here. Alright, so anyway, here's where we actually start implementing our function and seeing if our algorithm actually works. So the first new thing that you're going to see here is actually the include and in double quotes kms header.h. What this does, and this is a pretty common thing you see inside of C files, particularly if you ever start developing for iPhone, you're going to see a lot of header files. Basically, instead of including all of your integers and all this other stuff inside of the function itself, so instead of inside of int main or up top here, which would make it a global variable, you simply include a call to the preprocessor and say paste in all of this code. So it's going to take all of this and paste it in there. That just cleans things up a little bit. It makes it a little easier to read without having to declare all of our different data types. Again, you see the time being put into the the orange color. Again, that's because time can have a specific meaning in programming languages, but I'm not using that here. The next new thing you're going to see here inside this header file is the function prototype. And as it says in my little comment, C normally executes from top to bottom. So normally, if you want to declare a function that you're going to use later on, you must put it above where you are going to use it. So in this case, if I didn't have the function prototype, I would need to have this entire function here put up top before I could ever use it. By declaring a function prototype, I'm telling the C compiler, hey, I'm going to be using a function somewhere in here. So make sure you know that, so whenever I call it, you can go looking for it rather than thinking that this is just something that popped out of the blue here. So that prevents the compiler from returning an error. Next up, I have the define keyword. This is another preprocess command. Define creates a constant in memory. And constants have two advantages. The first is some people think it's easier to read constants. So miles per kilometers, this is probably never going to change, right? This is a constant. So I don't want to convert this. I never want to be able to change the value of this, first off. And then secondly, this is more memory efficient. Whenever you declare something as a variable, you're doing two things. The first thing you're doing is you're storing, or you're reserving memory for however many bytes that particular variable has. The second thing that you're doing is you're also reserving a certain amount of space in memory for it to begin converting back and forth. Because the variables can change, it needs to have space in memory in order to perform operations on your variable. So by defining a constant, you are limiting that, and you're making it more memory efficient. Now you'll notice it's in all uppercase. That isn't actually necessary. However, in order to prevent confusion, because whenever you use a constant, if you try to change this, it's going to throw you an error. It isn't necessarily, strictly speaking, to have it in all uppercase, but that's just a common convention. Just so other programmers looking at your code, if they run into this, they know that this is a defined constant. Now, as you're seeing now that we're moving files out of the main file in order to keep it smaller and cleaner, it can become difficult to know at a glance. You know, if I had several C files and I defined some of the constants in other places, it would be hard to know where this is. So that just gives a visual clue really quickly that this is a defined constant somewhere in the code structure. Next up we have int main and type void. You don't actually have to put the void in there. You can leave that off and it'll assume that you're returning void, but I'm putting it there just to be explicit. And then we have our print function, enter the amount of kilometers you ran, new line return. It gets distant kilometer, so it scans in, stores it into a placeholder, and then stores that into the address. And then it does the conversion, so the miles equals miles per kilometers times kilometers, and we already know that works. We've tested that. Then it prints out to 2 precision on the floating point the number of miles that is. So if we didn't do that, then it would print out 6 strings. It would be, incredibly overly accurate miles ran. The next thing it does, though, that's new, is this is how you actually call a function in C and in JavaScript, and in a lot of programming languages this is the general format for how you call a function. You say the name of the function and then you pass in the arguments to that function. In this case, what I'm passing in is this miles, so that's going to pass that right here. So then I have my void function. So void is a special keyword. It is a data type that basically means don't do anything. I'm not expecting to return anything, so here inside the int main I'm returning the value of 0 back to whatever called this. With void I'm not returning anything back, so the program that I called this from, I'm not expecting to return anything back into the int main. One of the key things here is that the name of the parameter, and that's what this is called, these are the parameter arguments. The name of the arguments in the parameter can be different than what you pass into it. So this is passing in really whatever I get out of this. So in this case it was what, 3.0 or 3.1 for the number of miles in a 5K run. It passes that value, so basically it substitutes 3.1K into here, and I'm telling it that I want this type to be of type double. After that I have a couple of integers that I am both declaring and initializing directly in here, and I am storing the value of miles ran into a second value called distance in miles. You don't really have to do this step, but I am doing it simply because I think that this is, whenever I start performing calculations distance in miles, it's a little easier to understand what it is I'm doing. But in such a short program you really wouldn't have to do that. So then the next step is I'm printing out input your minutes first when prompted, then any seconds left over. So this is dealing with getting the user to properly display data, because we don't know what the user might try typing in if we didn't explicitly tell them. So if we say enter your runtime, what would they do? Well, they could say something like, well, I ran the 5K and it took me 15.15 minutes, and they might mean 15 minutes and 15 seconds for that, or they might have gone ahead and done the conversion in their head and said, well, there's 6 seconds, and so this really equals what? 15 seconds? No, it's dead wrong. This really equals 9 seconds. So they might have done that conversion for you, or they might try entering in like this. In other words, you just don't have any clue of what they will enter in if you're not being very specific about what you want them to do. Now when we get into the next part of this, we're going to talk about if, else if, and other such control flow statements that allow you to check to see what the user has actually done. But here we're simply printing out the value, or excuse me, we're just simply printing out a string that tells them what it is we expect them to do. So then we actually ask them how many minutes did your run take, and we store that into an integer, time ran in minutes. Then we print out how many seconds did it take, we store that. Then we do the minutes per mile equals time ran in minutes divided by distance in miles. Perform the same thing, same calculation again, and then we echo that out. Alright, so let's run that. KMS2 miles. Oops. Oh, excuse me. There we go. So we know the value of a 5K mile should be 3.11. We got that. Input your minutes first. And so we'll say 20 minutes and 15 seconds, or 15 seconds, sure. And it tells me we ran 1 mile every 6 minutes and 31 seconds. And you can get your calculator out and make sure that is correct, but I think it is. At least it passed whenever I did the data checking. So that's our first way of writing this, but there's a lot of stuff that sucks about this code, and that's that I've intentionally done a lot of extra markup just to demonstrate it, but really almost all this is unnecessary. So whenever we jump back into our thing, we do a further refinement and we say, most of this stuff really isn't necessary. All we really need is the distance in miles, the time ran in minutes, time ran in seconds, and we just need to perform our our division on that and then output the values we get back. So in that one we ran KMS to miles and we refactor it. Alright, so now we have our refactored code here. The initial part, that's perfectly fine. And I had a few more comments on this one when I was looking at it. The next piece here though is I've cut down on all the different seconds conversions, and now all I'm doing is I'm inputting how many minutes did it take, how many seconds, and then I'm doing the division and then printing out what that is. So this is a much simpler way to solve the problem. So this is called code refactoring. This is one form of code refactoring really, and that's just enhancing the algorithm just to make it it's a little more, it is more memory efficient because I'm performing less operations, less calculations, so it will run faster. And the second advantage I get is it's easier to read. You don't have to sit here and figure out all the different math. So why did I do all that math? Well, I wanted to show you a couple of the different operations available to you inside of the C programming language. So that wraps up this tutorial. This is just a look at functions and sort of how they work using function prototypes, creating your own header files, defining constants that you can use. In fact, in a few places, well, particularly in my unrefactored code, there was a lot of places I could have used constants to save a little more memory. But anyway, that's how all that works. And again, I tested all this code out using base calculator. There is a little bit of a trick to base calculator. I don't know if I demoed this in other videos. That isn't going to work. Alt-T to fire it up BC, and I will show you one very quick gotcha, and that is what BC calls scale. So this is the number of significant digits calculated after the decimal place. So if I say scale equals 5, and then I do something like 47 divided by 53.0.88679, so it goes out to 5 significant digits. If I say scale equals 8, perform the same calculation, and you see it now goes out to 8 significant places. So depending upon the amount of precision you need, you may need to check that your scale is correctly whenever you use BC to do some quick desk checking to make sure that your variables and your algorithm actually works the way you think it will.